Hello students, this is the third of 4 videos helping you to solve free fall problems. The first is just an explanation of free fall in general. This is the second sample problem. In this problem we will be looking at determining how long it takes an object to fall when we know the distance that it falls. That's another typical type of free fall problem that you will have to solve. So the problem that we're solving is listed here. The observation deck of a tall skyscraper is 370 meters above the street. Determine the time required for a penny to free fall from the deck to the street below. I think it's worth noting that this is not a realistic scenario. Pennies have such low weight that the air resistance stops their acceleration fairly quickly if they are falling any kind of a significant distance. They reach a terminal velocity, meaning that the air resistance is pushing them up as hard as gravity is pulling them down. They stop speeding up after that. This problem assumes that that doesn't happen. This problem is not taking air resistance into account. So in free fall, we're assuming that the only force acting on the object is the force of gravity. There is no air resistance, and so we're assuming that the penny will speed up during the entire trip, 370 meters, as it falls. That's not very realistic, but that's what's happening in this problem. The 370 meter value is the delta x value, the displacement. We are taking down to be our positive direction, so the displacement is positive, and the acceleration will be positive. The object is speeding up as it falls downward at 9.81 meters per second squared. So that's going to be the acceleration in all of the free fall problems, even though it's not mentioned in the problem itself. We're assuming that the penny was dropped. Unlike the last problem where that was explicitly stated, that does not come up in this problem, but our assumption is that the penny begins from rest, that you're holding it, it's not moving, you let it go, and it begins moving. So our assumption is that the initial velocity is equal to 0. So these two pieces of information will not be stated in the free fall problems that you get, but you will need to make that assumption or you won't be able to solve the problem. If you look then at the information that we have the displacement, we have the initial velocity, and we have A, the acceleration. What piece of information are we looking for? You can see in the second sentence here, determine the time required for the penny to free fall from the deck to the street below. So time is the value that we're trying to find. Okay, so we're going to check off those pieces of information that we know in each of our equations. This is not a required step for problem solving, but this is a point at which lots of students get stuck. They don't have much difficulty reading through the problem, figuring out what they know, figuring out what they're looking for, even when some of the information seems to be missing, like the initial velocity or A. But sometimes students get stuck when they're faced with these 5 equations and they have to choose the correct one to use to solve the problem. So if you know right away which equation to use to solve the problem, then you don't have to do this next part. But if you don't know which equation to use right away to solve the problem, then this is a helpful device that will let you get to the correct equation. So we know delta x, and we know VI, and we know A. Okay? All right, so it's not possible to use the first equation to determine the time because we don't know the average velocity. It's not possible to use the second equation to find average velocity or final velocity because two pieces of information are unknown there. It's not possible to use the third equation to find the time because we don't know the final velocity. It is possible to use the fourth equation because we have all but one piece of information there. We have VI and A and delta X, so we could use the fourth equation to find VF squared. But that's not what we're looking for. They didn't ask us how fast is it going right before it hits the ground. So we're not looking for VF, so that's not a useful equation, although it is possible to use that one. It looks like the equation that we'll want to choose would be this last one, where delta x is equal to VI times t plus 1/2 AT squared. We know delta x and VI and A, and we're looking for t, and that has t as the last missing piece. Now, at first, when you look at that equation, it looks like it might be too difficult to use, as if you might have to solve it using the quadratic equation, because you don't know t, and t appears twice in the equation, here to the first power, and here to the second power. And a lot of times when we're looking for a value that appears twice in an equation like that, you need to solve for t, or typically it's called x. You would need to solve for t or x using the quadratic formula. But that's not actually going to be required for us because just like in the last problem, this term, VI times t, is actually equal to 0. So it doesn't matter what t is. We don't know what it is, but it doesn't matter what it is because no matter what it is, when you multiply it by 0, VI times t, the product of those two, will have to be equal to 0. So this equation is not going to be difficult to use to solve for t, even though when you first look at it, you might think, oh, how am I going to solve for t? It appears in both of those locations. This is a quadratic equation. All right, so delta x is equal to 370. And VI is equal to 0 meters per second. And I don't know what t is, but I know that anything times 0 is equal to 0. And then I have 1/2 times A, 9.81 meters per second squared, times t squared. So we'll simplify this a bit. 370 meters equals 0 plus 1/2 of 9.81 meters per second squared times t squared. So I'm going to simplify one more time before I actually solve for t by dropping out this 0, adding it to 1/2 9.81 meters per second squared times t squared. And I'm also going to take 1/2 of 9.8 at this stage. So 0.5 times 9.81 is equal to 4.905. So I'll simplify one more time. 370 meters equals 4.905 meters per second squared times t squared. Now, I can't really have 4 significant figures there, but I'm not going to round off my answer till the end. So I'm actually going to keep all those significant figures until I write my final answer, which is actually only going to have 2 significant figures because of the value 370. Divide both sides by 4.905. So t squared equals 370 meters divided by 4.905 meters per second squared. So 370 divided by 4.905 is equal to 75.4332, blah, 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 blah. I'm going to just write 75. Now, these meters are going to cancel out, and that will give me 1 over seconds. So the reciprocal of seconds squared. So 1 over seconds squared is seconds squared. But we're not done yet because this is time squared. They asked us how long does it take. We can't leave it as t squared. We want to find t. So we'll take the square root of both sides. And so I always find with this calculator on my computer that it's easiest to take the square root by raising the number to the value of the 0.5 power. But you have a square root button on your calculator that's probably easier to deal with. So if I take this to the 0.5 power, that's the same as finding the square root. That is 8.685 on, and I just have two significant figures, so since it's 8.68, I'm going to round that up to 8.7. 8.7 seconds. All right, so how long does it take a penny to fall 370 meters, assuming that it's accelerating that entire time, that it's not being acted on by air resistance, pushing it up or slowing it down? It would take 8.7 seconds.